Hi, my name is Wenhui Zhang. This is like a project collaboration with like lots of teams, especially Intel. We are gonna to thanks for the help and like contributions from Intel, and also we collaborate and talks with some professors as well, who are the first initial coding contributors to the MA, and also we talk with AMD a lot. So like when we upstream eventually, we want to make sure that the code won't have conflicts with each other. So thank you all for all the collaborations and discussions and all the contributions to the code. So today's topic is about extending integrity measurement architecture for attestation, especially for a cloud native workloads. So the talk is gonna to follow this a procedure. We firstly want to talk about a problem statement. We'll discuss the current status of attestation in TEE to support the cloud native scenario in cloud native scenarios, and then we'll give out limitations of the current available attestation frameworks in cloud native scenarios. So after we point out the current limitations to for our production workload, then we will summarize our key idea of supporting using extending the integrity measurement architecture for the workload attestation in CC in cloud native scenarios. Then we will dive into details of how we actually do it. Before we go into the detail, we'll review some backgrounds of the integrity measurement architecture. Then afterwards, we'll explain and have a deep zoom into our 4 contributions. The first contribution is RTMR backend to support the TEE, and the second contribution is a digest list to support attestation and extend the trust chain from the Linux kernel to the trusted domain. Then we'll discuss what the trusted domains we think they are, and how could we do attestation for them. Then in one of the attestation, one key component is a trusted container launcher, which is still in progress. So we'll discuss our design and our initial thought for the trusted container launcher, and we have a engineering schedule for the fourth point, and we will release it by the according to our roadmap. So we'll give a summary afterwards. So firstly, we'll go zoom into why do we want to use the integrity measurement to support cloud native workloads. So firstly, we know the boot sequence of the cloud native workloads is like this. With the BIOS, which is under the static root of trust, it initiates a grab, which performs a static root of trust as well. Then it uses a trusted boot to load the TDX module, which is a firmware, and then build a time measurement register from there. Then from there, the bootloader also loads the tboot will load the kernel, which is performed in a dynamic root of trust way. Inside of the kernel, we have 2 parts. One part is a disk. The other part is when we load the memory, when we load the information or the code or binary code into the memory, we use a init procedure to load it from there. And after the init procedure, then we'll have a daemons like a systemd and other daemons which are routinely run on the Linux. Then some of the daemons, they are cloud native daemons, such as Kubernetes, and also some network daemons that support Kubernetes, and our container shim and container dish daemons. They're the daemons running constantly on the node. And one of the daemons, like a kubelet, and like a container D, they will load the container. They will pull the container image and load the container image into the memory. These are the two steps, key steps in the container cloud native scenario. So inside the containers, we have the sidecars and applications run inside of the one containers or in separate containers. And sometimes in the fast scenario, the sidecars will in the runtime, it will accept the requests and initiate the workloads from there. So this is the chain of trust, or we should follow and establish for cloud native workloads. So after we know we should build this kind of chain of trust. So what type of what is the current status of TEE right now? Currently, in the TDX, they already supported TDX 1.0 and TDX 1.5. TDX 1.0 supports the TDX get info, get report, RTMR extend, and also support the VM call. So these ones in TDX 1.5, it also supports TD verify. So and there's also some support, kernel support, which are built on top of the architecture support. So they separate in the kernel support, they separate the TDX module call into two parts. One part is like a TD call to support the TD call, and the other one is like TDS hypercall, which will support further support the shim call from there. And on top of that, I think Intel, our collaborator team, they already put some upstream interface there for mcall and hypercall, which we could use. One call is to get a report. The other one is to for us to get a code in the TDX.c driver. Then there's however, the current TEE support, they have some limitations. For example, they only support secure container level or VM level attestation, and this will introduce IO bottleneck, and which does not enable and support our container workload scale up. And also due to we can't also is unable to scale out in larger scale as well for faster performance. Two a representative for the cloud native scenarios which support TDX right now. One is CNCF and Coco, and the other is KubeVirt. I will say they are very good and awesome projects. However, introduce some limitations where we want to adapt it into our internal workload. So our goal here is to support attestation for cloud native deployment. So what we are going to do here, we want to support several containers in one CVM, and which will in return make the IO bottleneck lower. And then we should support a tested class of containers, because lots of times we want to support dynamic resource allocation and scale out the containers through warm pool and PS tree fork. And also sometimes, most of the time, we want the containers to scale up directly, and which will actually should be supported by the container CRIO, which is a snapshot. And we want these functions to support. So to support this, we came up with a project with Intel, and we came up with a trust chain like this. We make the workload as the concatenation of the measurement of the VM, which in some cases is called a secure container, concatenate with that measurement of the trust domain components. And in one of the trust domain components is called trusted container launcher. We'll concatenate that one as well, the measurement of that one as well. Then afterwards, we'll concatenate the applications. So such as a model as a service applications or database applications. So our key idea here is to how could we extend the attestation from the VMs up to the workload and also to the dynamic loadable driver modules as well. So the key idea is to extend the IMA for workload attestation. This work is focusing on enabling the measurement for trusted domain. Key contributions are focus on enabling measurement for this trusted domain. And the trust chain boot is like this. The Intel will assign the certificate to the Intel TDX module, and which will then assign the signatures to the OBMF, and then it will attest the VM motion image. And the VM version image is rewrite by our CVM2. CVM rewriter will put our trusted domain into the CVM. So when it is booted, the IMA will automatically put everything into the trust chain and verify the test from there. So it will also test the integrity measurement architecture. Afterwards, it will test the container image bootloader and the container loader as well. So after the container loader image is put and the container loader is initialized, it will put the information into the KBS and join function from there. So I will probably skip the background here and then join into the contributions. So first is the RTMR background. The Intel part, they added our collaboration team added extend that RTMR and get report 0 and the verify report to support the attestation report. And then we also added a CCL recording event log for the kernel support in the VTPM driver. And because IMA initially will attest all the components in the Linux kernel, and it supports more than 10 hooks beforehand. And we found our trusted domain are only configuration files and executables, and also some KO files as well. So we want to limit IMA hooks for attestation in IMA BPRM check, IMA file map, and IMA file check. And we still follow IMA procedure and put the digest policy and digest policy measurement in the IMA folder. And our policy format is like this. We put customers we will specify the BPRM executable files, configuration files. And the digest list measurement will start with RTMR concatenated RTMR1, and which is extended to the PCR 8.2.15, which is mapped to RTMR2 in the VTPM driver. We are now following the IMA measurement list format, and we will convert to canal log event log and IMA log to CCNP event log as well. So the digest list right now is support local attestation. We write the CVM's golden values of the trusted domain files into I version, and register the file hashes in the I version fields as register from there. And this code is done in the CVM rewriter. And then in the kernel, when the kernel is booted, it will do the local attestation from there. And we are still working on a remote attestation support, which is a register golden value in the remote attester and attest it there. For the trusted domain, we added NVIDIA KO and container D, container shim run VC, run C, etc., and our CCNP products like CCNP user space attestation tool and KBS, etc. And also we are still working on writing the code for trusted container launcher, which in the Kubernetes part we added the container image loader, and in the container D we will add the container launcher from there. So the golden value in the attestation, the golden value of the container images, and also the such as language, the artifacts for the language models will follow SPIFFE SVID and protocol and the containerd command with container name will be attested as well, which is like using the pod ID dash container ID. So this is like a summary. Our code are actually like in progress of putting the CCAPI project, and it's supposed to be like in production ready for large language models workloads and database workloads by end of June, and we'll push it to the upstream afterwards.